Greetings. So today we will continue on our lecture regarding the op-amp circuits. And basically today we will talk about more examples. Let's talk about the voltage adder. So we will be in this chapter just considering the linear circuit. We are not going to discuss the non-linear circuit. So we can call it this the voltage adder or summing amplifier. Okay, so the circuit looks like this. So we basically can utilize the op-amp to perform addition between two voltage sources. So for example, this R1, this is RF, and this coming from input V1. And we can have another voltage source here, V2, with resistor R2. So with this configuration, we can basically add the voltage V1 and V2 at the output with a certain ratio. So what is going to be the output here? We will basically, forgot to add the virtual ground, the positive terminal. So here we will have two currents, I1 and I2. Both of them, they will be summed at this node here, and they will flow. So here we will have I1 plus I2. So I1, considering again, remember, since this amplifier have a very large gain, almost approaching infinity, the two terminal, they will be almost equal to each other. You remember from the last lecture that V out is basically equal to A0 V plus terminal minus the V negative terminal. So if A0 is almost infinity, this means that V plus minus V minus, they are equal to V out over infinity, which is almost equal to 0. So therefore V plus equal to V minus, assuming that again A0 or the open loop gain of the amplifier is infinity. Now therefore this node again, it's acting as a virtually ground. It's not a really ground. It's not shorted to 0. We have to stress out on this thing. So it's not shorted to 0. It's just carrying 0 potential due to the large gain of this amplifier. So I1 is equal to V1 divided by R1, and I2 is equal to V2 divided by R2. Now both of them, they will be summed together. So V out is equal to minus RF times V1 over R1 plus V2 over R2. Okay. Now you can see if R1 is equal to R2, sorry. R1 is equal to R2, then V out will equal minus F over R V1 plus V2. So you can see now we have here a summing between the two voltages V1 and V2, and we can set the gain or change the weighted sum of those voltage sources. We can also add multiple, can add furthermore here, so V3 with the R3, so as much as we want. Okay, so this is one of the applications that's very useful for us. Now let's take an example. So we're going to find the gain, find the closed loop gain. of this amplifier. So the circuit looks like this. This is a positive. So it's a non-inverting amplifier. A0 is almost infinity, and the negative is connected like this. We have multiple resistor networks here. Okay, and this is V out. So this is R1, R3, R4, and R2. Okay, so we want to find the closed loop V out over Vn. Now, life is easier here. This question is simplified, assuming that A0 is equal to infinity. So we can just equate that the V positive terminal equal to V negative. This is given that A0 is almost infinity. So now we need to find basically this point Vn and negative here. And it's going to be formed through 2 times a voltage divider. So first, let's find Vx over V out. It's basically going to equal to R4 in parallel with R3 plus R2 divided by R1 plus R4 in parallel with R3 plus R2. And after this, yes. So this is over V out. Now I want to find Vn, or let's just take the V out on the other side here, multiplied with the V out. Now Vn2 is another voltage divider now here, and this network here. So now all of this is Vx, Vn2 or Vn negative. Vn negative is basically R2 over R2 plus R3. Okay, as simple as that. And this is multiplied with the Vx. So now V positive is just equal to Vn, and the V negative is equal to the entire distance, so R2 over R2 plus R3 multiplied with the Vx, which is the entire expression, R4 in parallel with R3 plus R2 over R1 plus R4 R3 plus R2 and multiplied with the V out, and this is equal also to Vn, because V positive is equal to negative. Okay, so now in order to write V out over Vn, just taking one step ahead. So V out over Vn, I'm going to divide by all this, 1 divided by all of this. So it will be R2 plus R3 over R2 divided by R1 plus R4 in parallel with R2 plus R3 divided by R4 in parallel with the R2 plus R3. So here again in this example, the trick was to find 2 times voltage divider, and then you will be able to equate the 2 terminals, and reach to the gain that we are looking for. So again, R1 with R4, R3, and R2, they are forming a voltage divider. We find Vx, and then another voltage divider from Vx to reach to Vn negative. Okay. Now, let's just go back here and ask a question, what's going to happen if R1 is approaching 0? So what is going to happen again if R1 approaching 0? This means this is going to be shorted here, and this node Vx is just equal to V out, and then we will continue with the second voltage divider. So it will become very simple. So if R1 is equal to 0, and we will just have this small circuit. This is R4 and R3, and here R2. Sorry, this is the negative terminal. And this is Vn, and this is V out. Yeah, so basically this node is also equal to V out. So the presence of R4 is just like a load for the amplifier. It's not in the feedback, so it's not going to be doing anything. So we will just have a simple non-inverting amplifier with the gain equal V out over Vn. Again, you can derive it very easily with this voltage divider feedback, just from V out to reach here to Vn negative. And we will get V out over Vn equal to R2 plus R3 over R2, and this gets simplified to 1 plus R3 over R2. Just a conventional non-inverting amplifier. Now this is one more example. And again, we want to find the closed loop gain here, assuming A0 is also infinity. So the circuit looks like this. What type of amplifier? It is an inverting amplifier. Why? Because we are connecting, the input is coming through the inverting terminal. So this is R2, this is R3, R4, R1, and here we have the V out. Okay, so we can call this node as Vx, and we need to now find out the gain V out over Vn. Again, the current that is going here, I, since this is going to be act as a virtual ground because of A0 equal to infinity, it's going to force the two terminals to equal to each other. And now we will have I is equal to Vn divided by R2. And after that, we need to find how Vx is related to V out. So it's again a voltage divider. It will be R3 in parallel with the R4 divided by R1 plus R3 in parallel with the R4 times V out. So now what we are going to do is that we want to find how V out is basically related to this. And we are going to do that. So the current that flowing here is just minus Vx over R3, because this voltage, this is here a virtual ground and here Vx, so the voltage across R3 is just Vx, or the direction of the current is opposite. That's why we put a negative sign, and this is equal basically to Vn divided by R2. So now we replace Vx with this expression, so we will get minus R3 in parallel with R4 over R1 plus R3 in parallel with R4 multiplied with V out equals to Vn over R2, and therefore V out over Vn equals to minus R3 divided by R3, 1 multiplied with a minus, or let's call it a minus 1 multiplied with this thing. Okay, so it will be minus R3 over R2 times R1 plus R3 in parallel with the R4 divided by R3 in parallel with the R4. Okay, so you can see here the trick in this question is just to find how the V out is related to the how we can find V out in relation to Vn through the feedback path. Most likely it will go, you need to find either through Kirchhoff voltage law or Kirchhoff current law. Like, it won't go beyond this. Now let's take example. Again, assuming A0 is infinity, let's find it again here. So this is Vn, this is V out, R1, C1, C2, and R2. So again, because A0 is infinity, so the positive terminal is equal to the negative terminal. And we will also assume this is a virtual ground. So we will have Vn divided by R1 in parallel with a 1 over C1s. This is equal to V minus V out over 1 over C2s in parallel with R2. So V out over Vn equal to minus R2 in parallel with the 1 C2s over R1 in parallel with the 1 over C1s. So this is the gain of this circuit. Again, the current that is flowing here will continue to flow into this, the parallel combination of R and C, exactly the same. Now, just one point here. In most of the example, we are assuming A0 to be infinity, and we're finding the gain in that case. In case A0 is not infinity, just if A0 is not infinity, what you are going to do, you will go back to this relation that V out equals to A0 times V positive minus V negative. Okay, so this is always, let's say, valid. This is always true. Okay. When this is A0 is infinity, then it makes the problem easy, and we can assume that V positive equal to V negative if A0 is infinity. Okay, just keep this in mind. Now, I want that we should further discuss and applications of the op-amp. We can use them with the feedback resistor and capacitor to act as filters. We call them active RC filters. We can form from it a low pass filter, high pass filter, band pass filter, and other filter types. And we can have first order, second order, and higher order filters. So typically we have first and second order, and if you want higher order filters, you cascade multiple of these filters in order to get the order that you want. For example, if you want a fifth order filter, you can cascade first order with 2 second orders. Then there will be a total of fifth order filter. Let's take a simplified cases of those filters. You can have in different configuration, you can still perform the filtering operations. So if, for example, I have this configuration, and this is R1, and this is C1. What does this remind you of? It's basically the integrator circuit that we discussed last time. Now, if I have a resistor further here, so excuse my drawings. And this is V out, and let's call this R2. Okay, now assuming that A0 is infinity, we again can simplify the problem. And basically the gain is going to be V out over Vn equals, you can derive it yourself, but it's basically the same. So it will be minus 1 over R1 multiplied with R2 in parallel with a 1 over C2, C1S. And this will equal to minus R2 over R1 times 1 over 1 plus R2 C1 times S. Now this is the transfer function of this circuit. Let's look at it more carefully. So if I want to plot the Bode plot of this one, so this is log F, and this is 20 log of V out over Vn. So at DC, I will have 20 log of R2 over R1 in dB. And I will continue straight until I find the pole of this one that occurs basically at 1 over R2 times C1, and then we will decay with a slope of minus 20 dB per decade after reaching the first pole that we have here. So you can see that this shows you what type of filter. So we are passing the low frequencies with the good gains, while the high frequencies, they are facing attenuation. So this is act as a low pass filter. You can see it gives, you can also set the ratio of R2 over R1 in or to 1 if you don't want any amplification in your signal, and you can as well set it to higher than 1 if you want to amplify your signal in the bass band. Now let's see what other filter we can have. Okay, let me show you this one. So we have Vn here, we have C1, R1, and I have R2 here, V out. Okay, again, assuming A0 infinity, we have V out over Vn the same way. This is a virtually ground. The current going here will continue here and exactly the same way. So we will have minus R2 over 1 over C1s in parallel with R1. Now this I did it fast, but I assume that you knew, now you know the trick, so or the procedure for solving. So it should be straightforward. So the gain will be minus R2 C1s over 1 plus R1 C1 times S. Again, if we want to look at the body plot for a log F and 20 log of V out over Vn. So we will be we have a 0 at the origin, and therefore we will increase with the 20 dB per decade. And once we meet the first pole located at 1 over R1 C1, we will continue with a flat transfer function. So you can see now we are attenuating the low frequencies and passing the high frequencies, which tells us that this is acting as a high pass filter. Both those two filters, they are a first order filter. Now you can have a more complicated, let's say, network around this op-amp to form second order filter. Okay. Now I just wanna share with you an example. Show you from close the share here. I want to share with you my screen of the computer. Sounds okay. Excuse me 1 minute. I basically want to show you an example here that we are utilizing a filter to perform some operation on the signal. So we want to get rid from the noise that is coming in some audio or some song. So let's listen to this song here. Let me see. So I want you to hear first this one. So this is a noisy signal. Okay, so basically there is a noise of wind noise that is lying below 1 kilohertz of frequencies. So again, just focus and listen that there is a wind noise. Okay, now this basically audio signal, we are taking it into our LT-SPICE simulation. So what do we have here? We have a band pass filter formed from a low pass filter stage followed by a high pass filter stage. Both of them, they are second order filters. So that is different from what we just discussed here. It's a bit more complicated. You need to, for finding the transfer function, we need to have more of a Kirchhoff voltage laws and KCLs as well. Just want to show you first the AC transfer function or the simulation of this filter. Okay, so we want to run the AC analysis and I want to see the V output. Why you are not coming? Something wrong is happening here. Okay, let me double check what's wrong. Okay. So now we can see this is the V output. So it's a band pass filter with the cutoff frequencies more than 1 kilohertz, little bit, and until almost 3 kilohertz as well. So it's a very small band. Now we have here in this input source, we are entering the wave file, which has the sound coming signal. And now we want to run the transient analysis. So let me just stop the AC and run DC analysis. Sorry, this, or let's say, statement here is basically to save the output voltage as another wave signal that we want to listen to it. So now we just want to run transient analysis. And this is the output waveform coming. I mean, we cannot understand what's happening. We just want to make sure after listening it again that we get rid from the wind and noises that's coming. So after it's done, I'll play it for you. Okay, let's play. I also added some amplification for the output signals. So let me just play. So scary noise. Let's remember. So this was the original signal. You can see that you just need to differentiate which one is the wind. So we have got red from the wind. There's still some noises there, but not the wind noise, which we have removed with the filter. Now you can change the frequencies and see that if you have a corner that's lower than that, then part of the wind noise remains there. So these are kind of the applications that one of many applications that we can use the filters on. You will see that you will need those filters for the comlinks engineering application that you will be soon working on it. Okay, I think we can stop for here today and we meet in the next lecture. Bye.